recording this to the cloud. Now, this is a few days before Thanksgiving in America. Normally, it would not be the last class of the semester face-to-face. We'll still be meeting online, but it just happens to be. It just happens to be the last face-to-face.
Where I need to put your chicken bones.
I hear some voices in the background here. I'll have to get some people muted if you could. So I brought with me a little pizzazz here tonight, since it is the last one. I don't have any viable alcoholic beverages right now, but I could go down and get them. But I want to say thank you to David for coming tonight. We've brought along the party balloons and hats and all sorts of things for you, because we've been waiting with bated breath just to see you arrive. Because I've been telling my students every week, this is the Renaissance man of educational technology, online learning, gaming, any learning analytics, anything that you want to study, evaluation of systems online, all sorts of stuff. David's been studying them, and we'll get into that in just a second. But again, this is kind of like week 13, 14, I guess, the start of week 14, and we only have 15 weeks. And week 15 is for sharing what we've accomplished this semester. And so this is the last time in which we'll have a guest in on this class. Thanks for Chris Stevers coming to us tonight from Northern Indiana. And Dr. Chris Stevers, Dr. Ziheng Xiao, my former advisee, has joined us from Eastern Indiana, from Richmond, Indiana, unless she's down here in Bloomington. My former advisee, Jennifer Park, is with us from University of North Carolina at Wilmington. And then Yayoi Enzi is with us from Japan, and I'll see Yayoi in Japan in 10 days or some 11 days, along with Amelia there. They'll both join me on the western slopes parts of Japan, exploring and so forth. So I'm glad to see a lot of folks in here that have joined us for the final event. Now, I have a prize for all of you who are attending, and maybe I can announce it today, I don't know, but I have something I'm going to give to you, a little memento of this entire class. Because as some of you know, I think Christy knows, a couple of you know, Bo knows, Bo always knows, I've been creating YouTube videos of every week and made it into a playlist. So every single guest that we've had this semester, I got 18 of them, I've counted. They're in a playlist that you get to take with you from this course. You get to keep that and share it, whatever you want to do, and review this. And what, you know, again, use as you would like. So Mink Young's with us, another alum of our program from Western Florida, the University of West Florida. William Kanye is with us from the Business School at Indiana University, Bloomington. Hi, William. Good to have you with us here, William, another advisee of mine. So we've got a lot of folks with us. Some people who are currently working on dissertations, like Rachel Herman, and other people who've finished their dissertations, like Trung Phan, who just showed up here from Cal State Fresno. So we've got a lot of alums, friends of friends. I count 25 people. And now we have another alum, Elliot Jordan's joining us, who's a big gaming person, David. So I'm going to stop talking for a second. And what I want David to do is, it's not possible to summarize your career in 1 hour, but I'm going to have you try and do it in 1 or 2 minutes. Can you kind of give us the overview of where how you've traveled within this space since you got your doctorate at Vermont, University of Vermont, and where you've made your impact? In particular, what I'd like you to talk about is what you were doing at Curtin University in Western Australia, because it said you were running a center. And I know my friends down in Melbourne and Sydney and so forth, they're running centers. They're always called digital future centers in Australia. They like the future stuff. Was it one of those? So please tell us a bit about your adventures during the past couple of decades in this space, and then we'll have you present your recent paper on AI theories. David.
All right. Well, thank you so much. I know that you're all aware of how lucky you are to be in a class with Curtis Bonk from week after week, with insights and connectivity across the world, across the globe. So
I don't know. They're ready to beat me up with one of these. I don't know. So
the very first time I ever saw Kurt give a lecture It was at a national conference, or I think it was a national conference in the US. And I walked into the back of the room and found a seat at the back, and it was totally packed as his always are. And the very first thing he did was threw a rubber chicken across the room. And I thought, yep, I've found my mentor. I know someone that I really need to study with.
They like rubber ducks in Beijing, let me tell you. I had when I did that in Beijing, I had so many requests. I don't know what it was about rubber ducks in Beijing.
So it's a great pleasure to be here. My name is David Gibson. I currently have a title called the UNESCO Chair on Data Science in Higher Education, Learning, and Teaching. And we put that chair together when I was at the university, Curtin University in Western Australia. After my PhD, I did my PhD in a very interesting, it was interesting to me at the time. There had been a 5-year qualitative study of 5 high school sites in Vermont, trying to understand how change comes into a system and how it sustains, and which ones take over and become important to the site and which ones sort of die out and why. So there were all these, we were doing these in-depth interviews of schools that we knew that where there had been important changes happen. We said, how did it start? What happened then? Who took on the responsibilities and so forth. From that, I was studying at the time and just becoming aware of a systems diagramming software. I was introduced to it as Stella, and the guy that did it was from Dartmouth, but it really had come out of an engineering kind of background, and is now not just called Stella. There's several versions of it, but it's for systems diagramming, systems mapping, and it has a small iconographic vocabulary for things that are part of the system. And the thing that astonished me at that time is it almost had a physical sense to it, because I learned there that relationships between entities in a network might be information only, or might actually be a physical kind of relationship, and that the flows of physical to versus information were different. And so I drew these system maps of the changes as people told the stories. And the thing that was new to me at the time was that you could start from a story and you could quantify it. You could quantify people's understanding of the narrative. Nowadays, that is, it's much, much easier to do. And there are many more tools, and there are branches of mathematics that have sort of become established and are now more sort of easier to use and firmly there. But at the time, it was kind of an experiment on my part to see whether I could draw a mechanistic version of the stories in such a way that we could use those to predict how school sites would work. So, for example, that part of the story of most sites is that there was some kind of a spark. Maybe it was a teacher, maybe it was 3 people had gone away to a conference and came back with an idea. Maybe it was an external force from the community that caused it. Something caused everyone to pay attention a little bit, and that we called it spark. We also saw that there was a kind of cyclic fueling taking place. And this led to sustainable, the spark could sustain a small fire. It didn't necessarily burn across the entire institution. It might have just stayed inside a classroom, or maybe a couple of classrooms. So these were the kinds of things we were studying. And I did system diagrams using this software called Stella. And then we tested the diagrams by saying, well, in site number 5, could it be dialed up? In other words, could the game features of the simulation that I had made, the simulation map of the system diagram of their stories, could it be tuned to tell all 5 stories or not? And so that it led us to think that, yes, we could make a generic systems diagrams of the underpinning archetypal energetic relationships, let's call them, in a school setting, and tuned a certain way, they would act like school number 1 or 2 or 3 or 4 or 5. We could tell 5 different stories with one mechanic. So that was my doctoral work. Since
So-
that time,
So
I've kind of,
David,
yeah,
so I didn't do a good enough job of introducing you. So I'll just briefly introduce again. In addition to complex systems modeling of educational change, David is the creator of simSchool. He's also been involved in creating a classroom flight simulator for preparing educators, an eFolio tool of online performance assessment. Is that right?
that's right.
Mobile learning, game-based learning platforms. The list goes on and on. If you've gotten his bio from me, so you can elaborate on any aspect of those things that you might feel that need a little more explaining, or
Absolutely, and feel free, anyone, to question. You could put it into the chat, and hopefully Kurt or myself will get to it. And thank you for bringing that up, because the thing that's common to the story I was just telling you about systems diagrams, those really became game engines. So a systems diagram that's in a mechanistic system that's well defined is the same thing as a game engine, because in a game engine there's inputs, there's transformations, there's things that happen to the data, and then there's things that the user can do. So that got me very interested in game-based learning. The simSchool app that was just mentioned is a classroom simulator that has AI students sitting in desks, and we can model something like 9 trillion different student types in each chair. So you could have a classroom of 20 students that were very, very different from each other. And it's used in teacher education, special education, and it rests on a psychological theory, several psychological theories that are well known in the learning sciences. So it's not like I made it all. It was like I borrowed, similarly to what happened in the narratives from how change happens in a school. The theories from learning sciences are theories of how people believe things work. Those can be turned into game engines, and then that illustrative engine can act the way that the theorists said it should act. So I can get into a lot more detail with simSchool if you're interested in learning theories and psychology and AI in that vein. But tonight, what I want to tell you a little bit about is that in my own journey, I've learned that from the game engine, which it can just be the illustration of your own story, so it could be fanciful as well as untrue, and it's just going to be accurate to the story that you tell. Then you have the problem of whether that's grounded in some kind of reality and whether it's true or not. And the problem I really want to put on the table tonight is complexity, where even when you tell a good story and you think you know what's going on, there may be underlying parts of the mechanisms that are so complex that they fool us a lot. So part of my plan tonight is I'm going to show you a little spreadsheet model that was the one that really had that kind of got my attention. I had an aha moment because it's so simple. You can recreate it yourself, you can play with it, and you can understand a lot more about what's called chaos and complexity theory with this simple model. And then from there, jump to the article, because the article says essentially that because of what we know about complexity, can we now weave together the theories of individual learning, social learning, and cultural learning into one big model, or into a series of models that relate to each other at least. So that's kind of the point of the article written large.
That's important because this is a course on learning environment design. They've been reading about learning theories all along, here and there. It's not explicitly teaching them about learning theories. Those are other courses that do that. But in here, they've been reading about various ones and trying to make sense of them in a more eclectic approach is what you're providing to us in this article, which is, I think, in week 14 article list. It's the third article listed, I believe, and I think I highlighted it for those in my class. And if you didn't get this article from David, it just came out in British Journal of Ed Tech, Learning Theories for Artificial Intelligence, Promoting Learning Processes, with his colleagues. There are 4 of his colleagues co-writing this with him. So it's a pleasure to have you come in and present something that's just been published. That's great.
Yeah, the colleagues are from Hong Kong, Australia, and the US and Germany. So it's a little bit of an international flavor of people that we work with. It's very interesting that you say about learning design, because inherent in any design are hidden theories. So even if you don't think you've got a learning theory, if you're doing a lesson design or designing an experience for someone to learn something, you are embodying a theory in the design. The design itself and the theory of what's going to happen is your hypothesis essentially is, if someone comes in and plays with the things I make, I will teach them something, or they will learn something. So there's a very important connection between how we think things work and then the affordances we give to a learner or an explorer who's coming into the spaces that we create. A real big common ground with learning design is that it's all about the creation of a space where there's potential for learning opportunities. And in game design, it's very similar to that. You're creating in a what I would think of as kind of a frozen vocabulary, because if I'm doing a technical game, I've got only the current instruments and programming skills and AI of today to work with. These are limitations, but they also are the boundaries of the play space that we're creating. All the tools I give to the learner are the affordances. If I don't give them a tool, they can't use it. And if I give them a tool, they can only use it in the ways that the game is prepared to let them use it. Well, in an open-ended design for learning, something similar to that happens. For example, if you just say we're going to have a reading, and you think at one level a reading is a very simple thing. No, it isn't. There are some people who read very deeply and differently. There are other people who can't even approach the words. So you've got the affordance of the tool and its role in the space that you've created are very much in keeping with the kinds of things I'm going to talk about tonight. This relationship between the affordances and the realities. So
David, we already have a question for you.
Oh, very good. Let's go.
Rachel, go ahead.
So I put my question in chat, but it might need a little more explanation, or it might not. I don't know. Could simSchool be used to prepare? I mean, I know it's okay. I read about it, and it's designed to prepare future classroom teachers. Could it be used to prepare enterprise trainers? And what I really mean is, you said you started talking about the variety of students possible in simSchool. Could you create the students that are adults that have, other characteristics that a trainer in a business? Okay.
Yeah, absolutely. And there are a lot of questions similar to that. So as a flight simulator concept, imagine if you're going to build a flight simulator. So you build different kinds of airplanes that have different approaches. There's an underlying sort of ground truthing of how air works over an airfoil, that kind of thing. So in simSchool, the thing that was working like that is psychology. The psychology of learning. At the underpinning model of personality theory is a theory called the 5-factor model, the FFM, or sometimes it's also known as the Big Five, or it's also known as the OCEAN theory, OCEAN. So OCEAN stands for openness, and each of these are bivalent components or elements. So on openness, there's openness and closedness. The openness is I explore the world, I like new things. On the other end of that is I prefer to do things that I already know how to do and do well. So I'm less open to new experience, but I'm perfectly happy to use the skills I have. So there's good parts at both ends of each of these spectrums, and there are weaknesses at both ends. So that's openness. The C is for conscientiousness. A high conscientious person really likes to dot the I's and cross the T's. A low conscientious person likes to try everything new out and invent brand new things. So you can see there's a good part to that, as well as a challenge in each of those. That's the C. E is extroversion, and of course there's extroversion and introversion. Introverted people are quite happy to sit in a corner by themselves and read and absorb things by themselves. Extroverts really like to get feedback from the external environment, especially from other people. And then A, agreeableness, that's the A of ocean. agreeableness at the high end of agreeableness. They're very friendly. Everyone loves them. They're easy to get along with. On the low end of that one, more prickly, let's call them. But a really useful person who's on that end is a critical friend to have in a group, because they're going to stop the group action and say, wait a minute, we haven't thought of this. What about that and the other? So there's really good critical things happening at both ends of that one. And then the N stands for neuroticism. I kind of prefer to call it, it's fear related. Neuroticism is essentially, am I afraid, if I'm highly neurotic, I might not get exactly the psychological meaning of this, but let me just think of the low end. The low end of neuroticism is unafraid. But the bad part of that is I might be stoic. Nothing bothers me. A bomb could go off and I just don't flinch. At the high end, I'm very flinchy. I'm highly hypersensitive. Now, all five of these, and all of us are a mixture of these five, and not only that, we evolve moment to moment and context by context. So these are not traits in the sense of a long-lasting traits, they're states. So in SimSchool, the way you get to 9 trillion is if you put those five, just those five, without going into any part of the rest of intelligence, just this emotional underpinning. And let's say you have about a scale with 0 in the middle, +10 or -10 representing the high and low. So that gives you 21 positions on each of the five. So that's going to be 21 times 21 times 21 times, it's 21 to the 5th. So if anybody has a calculator handy, if you do 21 to the 5th, that's the number of different personality profiles that you can make with a system that uses those numbers. And so so the answer to your question anyway is exactly right. And in addition to ocean, I have sort of informally thought of ocean as the emotional layer. It isn't exactly emotional, but you notice it's a nonverbal personality underlayer level. So our emotions ride on top of it. But I kind of like thinking of it as the emotional layer. And evolutionarily, we evolved that. All animal studies, you can go to lots of mammal studies, focus on 2 of the 5, neuroticism and exploratory behavior, because if you don't explore, you don't find food. And if you are too stoic about the dangers in the environment, you get eaten or chomped on or whatever. So and the other thing that I could share with you that is not common in the literature, because people are just, I think, we don't know enough to be absolutely certain about it, but there are strong indications that the neurotransmitters in our brainwave structure is very highly correlated with these 5. The 5 have been established, by the way, in 41 different languages. So, and the way it's called the linguistic hypothesis, if you want to look this up and follow it along. And I remember somebody wrote me a couple of days ago that they were doing some linguistic work. So the linguistic hypothesis is that the way we talk about other people is a secret code in our language that encodes how we think about ourselves and others. So when we describe people, and all the descriptive language across all the languages tend to come down to these 5 factors, the 5-factor model, so that by the time you add up all the ways that we talk about each other, it's described in languages and so forth. So that's a little bit of news about SimSchool, how the model works. In addition to the ocean model, the Cattell-Horn theory of intelligence had a factorial model that included other parts of intelligence. Broadly speaking, intelligence has behavior and emotion and cognition. So what we've talked about now is the emotional layer, which is the ocean layer. There's behavioral layers, which are tightly fitting with our emotional, because our behavior in the world, like for the well, the baby who cries to be fed and cries because they're wet starts to establish the foundations of language in themselves and in the home, and in all the animal studies and so forth. The same thing kind of happens. And then the stickier issue of cognition arises on top of all that. Well, of that, what does the animal know of itself? So the whole idea of metacognition, do I take note of how I'm feeling and acting? And do I then also, can I take note at a time when I am not directly now acting and feeling and thinking and doing something? So can I project, in other words, and how far into the future can I project? So the simSchool model has features to handle cognition, emotion, and behavior, and then that just adds to the profile of what you can do with it.
David, is there a link for the simSchool project, or?
Yep, simschool.org, I believe, is the one. Somebody might give that a try. Just do simschool.org, see what comes up.
Bo will post the links here. I'll just point out we have a few psychology professors in the group with us. We have 31 people here now. And we also have a representation, 2 people from China, 1 person at least from Thailand, and 2 people from Japan. So we've got at least 4 countries with us tonight. So that's
fantastic. Oh, this is really, really wonderful. Yeah, thank you so much. And it doesn't surprise me to have a classroom like this, diverse and global and very interesting, all at once. All right, so should I kind of go into the first point I want to make about what complexity is?
Yeah.
All right, I want to share my screen to give you a look at a spreadsheet. And I will have to try to see how big I can make this so you can really see it close. So I'm going to start up in the upper right-hand corner in this square. And this little equation, r times x times 1 minus x, that's 3 terms. R is a landscape dimension. You might think of this as the affordances of your learning design. So the R is the affordance of your game or your space or your learning design. The X as a starting condition, you can think of that as what is the student bringing into the room. So they come in with history and gender and all sorts of things. So what we're looking at here is that the starting condition, and here we're forcing the starting condition to stay between 0 and 1. You know that there's an infinity between 0 and 1, so we are in an infinite. We're in an infinite universe here, but we're making the universe very small between 0 and 1, but we're forcing it to stay there. So we're saying that no matter where your starting condition is, where you wind up is still going to be in the universe somewhere. We're not letting it bounce out into a brand new space. And then the 1 minus x is the unity of where our interval from 0 to 1 is the unity of the universe. The 1 minus x is just saying, what were we before? Where will we be if we had the universe as it was? We're minusing our starting condition. What now has happened? So I'm going to now back up from this. So it's a very simple little phrase. But now what happens here? So if my learning condition is very simple, and my starting condition is here, you can see what's happening here. This is tending towards 0. It tends towards 0 very fast. And then if I make the learning condition a little bit more interesting, look what happens there. Now all of a sudden it has a feature that in the world of systems, and especially dynamic systems, this is called an attractor. So now the system has attracted up to a 0.5. You see how over here in the computation side, our history, by the way, is just these 2 long columns. So we've let it run for, think of it as centuries. So we're letting this system run for centuries. So at a certain point in time, the system just finds a stable point and it stays on that point. That's what an attractor does. Now, back here when the system was very small, it also was tending towards zero, but it never got there. So it might have had a long, long way to go. It might have needed a huge amount of time. And this is, it's going to be all different depending on the starting condition. When the landscape, when your learning design is extremely simple, the starting position doesn't matter too much. Here's a starting position that's going to be closer to 1, 0.99. Now notice that it did drop precipitously because we started up much closer to the edge of our universe, 0.99, but it still drops way down and stays at 0. Now, what I want to show you is that in the regimes of interest here, if we get to some interesting spaces, like I'm just going to put in a number here, now all of a sudden we're getting complex change. Notice that the main, the mechanic of this entire system is still the same simple 3 things: the starting position, the shape of the universe, and time. So the only 3 things in the whole thing. But now all of a sudden, we see at the beginning of this, there's these things called transients. They don't quite settle in, but then it does settle into something. But now watch what happens here. I'm going to go back to having a starting position that's quite different. Notice that the transients are the same, but it still settles into a sort of a repeating behavior. So this is called a cyclic attractor. We have point attractors like the 0.5. We have cyclic attractors. And then something very interesting that happens around 4.5. That's no too much. That's too much. 4. Let's try this. Let me do it this way. See if I can approach it. Here we go. So here we're approaching 4. The numerical universe here is that the fractal landscape has got to be between 1 and 4, otherwise it just bounces out into space and doesn't teach us anything. But notice what's happening here. There's a quasi pattern repetition, but not really. This is the beginning of complex behavior. And then we do get all the way up to chaotic behavior. So what I'm illustrating here before we talk a whole lot more about how this works in simSchool and AI and what it means for learning theory, the main thing that was the big aha to me from this very simple spreadsheet is that a very simple equation could have a whole lot of different outcomes depending on the starting condition and essentially the affordances of the space. So the space affordances, similar to learning design, similar to game design, similar to even the articulated narrative of something, will essentially come down to about 3 different kinds of regimes. There's the regime that dies out, like this one, and eventually goes to death and just never returns, doesn't have any behavior. It takes time, sometimes faster than others, over time, but eventually it just dies. There are cyclic regimes. This is the point behavior. Point behavior is similar to death, I think. Here's an example. In the range of 3, you can see that it's starting to sort of zero in. It over time, you would imagine this will zero back into the point. But the really fun thing in this world is that there will be many regimes with cyclic behaviors, some 2-phase, 3-phase, 4-phase, and so forth. So for me, this means that a single learning design could have 5 different outcomes on students. It doesn't have a single outcome on students. Depending on what they bring to the table, it cannot work at all. It can work to really excite them and move them forward. It could bring them to a new place. But it won't necessarily work the same way for everyone. And this is fundamental to our understanding of how complexity works. the last thing I'll say about this, and then we'll jump into other discussion. The way this is working, I can share this spreadsheet with you so you can play with it yourself. It's really a fun toy and tool. So as for those who knows how spreadsheets work, so this square is the R variable, and that's the first thing in the equation, times the X variable. And notice the X variable is changing over time. So it's X not just once and for all, but it's X today and X tomorrow, and then the next week and the week after that. So it's a changing X because every time it goes into the system, there's a reflective component. And this is one of the fascinating things to me about complexity, is that the thing that makes a system complex is a self-referential loop. And in learning theories, we call this self-reflection and metacognition. But it's the same, but mechanistically, every system that has a self-referential loop aspect, we know it's rampant in the brain. There are self-referential loops all over the neural architecture. And when we design something for people to learn and to work together and that kind of thing, if we don't have a self-reflective loop, we're missing the most important feature and for growth to occur. So just keep that little piece in mind. But that's the magic that's happening here, is that with nothing more than a shape or a shape of a space, a starting condition, and self-reflection, you get all this type of behavior off of very, very simple underpinnings. So let me stop that one and stop that share. Let me see if there's questions on that before I share with you the PowerPoint of the article. Yeah,
Any
good.
questions?
Thank you for showing the simSchool in the chat. So my point of all that is just that complexity is not a fuzzy subject. It's actually a highly quantitative subject that's connected with our qualitative understanding of how systems fit together. So it's a bridging behavior between qualitative understandings and our traditional tools. Oh, I should have pointed out, traditional statistics tools are of no help at all in that spreadsheet. I had a little section up at the top where it does the average and you can imagine that since we're studying things that change over time, because of that, all of the lines you can draw in it are only temporarily useful in short periods of time. Nothing that has a linear basis helps you out in the long run in a complex system. So we do have to rely on different ways of understanding the world and putting it together in order to really get the most out of our understanding. Now, those linear relationships are really helpful when you just have time one and time two. If you've only got those two, then having some linearity between those two and all the tools we're used to of statistics and all the statistical tests that we know all work just fine. But in the system that I was just showing you that has different simple outcomes, you can't predict those by using any kind of statistics. You have to have yeah.
We got a question from Suliporn in Bangkok. Is there any signal hinting when people recognize that there is a self-referencing loop happening?
Oh yeah, let me think about that. Is there any, say that again?
Any signal hinting?
Yeah,
when people recognize that there's a self-referencing loop.
Oh yeah, that's an excellent question. You know, in metacognition studies, and even if you think about assessment work in higher ed, assessment work is not finished until the person being assessed has understood the message. So, because otherwise the feedback is just going in over the head. So if I give you lots of feedback, even if it's fantastic feedback and would help you, if you don't understand what I'm saying or can't apply it, so there is a feedback loop itself between the entity and the system. And so one of the answers to that signal issue is there reciprocity between the whole of the system and a part of the system? If you don't have a reciprocity that's, if you can't see a reciprocity, then you don't know if it's there or not. And if you do have connections and there is none, then you're missing it. So, and there are systems that are designed that way, basic hierarchical systems. Our body's full of them. If I say, if I start feeling like I'm hungry, the rest of my whole system is giving me a signal. Now, if I don't pay attention to it, it just gets worse and worse and worse. It's not going to go away on it. I have to, in the real world, go out and do something to close the loop. Now, and by, eating a snack, that closes the loop. And then that starts the process again. So this whole idea in cyclic behaviors in particular, something is propelling it forward into the next part of the cycle. So everything that we know of that has a sustaining kind of feature to it, like a hunger, like a sleep cycle or a hunger and feeding cycle, you can think of it in a simple sine wave terms. And I think it's useful to think about our statistical problems in this way. So if we're at the height of the curve and the need's not there, there may be no signal. If we're heading downhill, there's one kind of signaling taking place in the system. If we're down at the bottom, there's another one. And so at each point in the sine wave, it's passing through zero only a couple of times. And that's the only time when you wouldn't have a signal of any kind. So yes, there are signals in the systems, and those come from all the different ways that we measure things. I once thought about doing an article, and I think I have addressed this somewhere, but I can't remember if I've really played it out. But going back to that sine wave problem, imagine that you were trying to assess a system in which, well, here's a simple system. Put a thermometer in a room, and the thermometer is set, and somebody comes in and out of the room a lot. So thermometer set for 65. Sorry for the folks that are in, I don't know what that would be in centigrade. And so the room is never exactly on 65. It's either a little bit hot and the engine's shutting off, or it's a little bit cold and the system's shutting on. And it's wavering around the set point. So the set point out here, which was externally set, is a driver for making the system work over time. And that's exactly what was going on in this one. So there are exactly four signals in a simple sine wave. There's the signal that, oh, the heater is on, but the room is too cold. Then the heater's doing its job. But then when it passes the 0 point, the heater is still on, but the room is hotter. Oh, well, you're wasting energy now. Okay, shut it off. When you shut it off, now the room is hot and the engine's not doing anything. Guess what? You got a free ride. It goes back through 0 though, and it starts getting cold again, and the engine has not come on yet. Oh my gosh, nothing's working. So you have 4 different outcomes assessing the same simple system. It's a very simple system with one set point and the thing swinging. And if you measured it on one day, day 2, day 3, and day 4, you might come to 4 different conclusions of the same system. And this is part of the message that I'm trying to get to with the complexity argument, is that don't rest on your laurels of one measure that told you one thing.
Right.
Think about what would have happened if it were another day or 3 weeks later or 6 months later. And is the system capturable given the way you're trying to get at it? Do you capture the full scope of the system? All of the influences in, all of them out? Or if not, how are you going to simplify it? So, and that's a typical thing that we do, and it works fine. Science is based on simplifying theoretically and in order to focus.
So
Great.
David, Bo said 65 is 18 in Celsius.
Very good.
And Bo has a question for you. Then you should probably go on to the article. So Bo.
Okay.
Yeah, I was just wondering. So my background is K-12 education. One of the things that we talk about is the difference between the terms complexity and difficulty. And I was wondering, the calculator that you just demonstrated for us with regards to complexity, does that would that apply in other areas of complexity, of measuring complexity as well? Like we talk about like depth of knowledge in this sense a lot, but I didn't know if this was just specifically in the terms of instructional design.
Yeah, well, that's very good, and I don't know if I have exactly the right answer for you, or even an answer. But let me point this out, that there's a difference between being complicated and complex. So the modern meaning of the term complexity is involved with whole system and agency and a relationship of a network of relations between whole system and the agency. Where in complicated, you could have a watch that's complicated, and notice that in a complicated system, if you go in and sort of tweak a knob and take out a nut or a bolt, that watch just stops. It's done. It doesn't do its job anymore. Highly complicated systems that are difficult are generally of that sort. They're stiff and they do not flex. But you go into a complex environment and tweak a knot and tweak something, it does not stop. It adapts or it evolves. And it might evolve and kind of wrap around the disturbance. In some cases, it could, completely evolve away from where it used to be. But these effects in a complex system, generally, they're closer to life in a complex system than being just complicated. But there's a shared space there, because the complexity also means, yeah, there are many, many features involved. But notice that we got to complexity with only 3 little features. We had, and that's what's really surprising about that model, is that you can get highly chaotic and full set of complex behaviors out of very, very simple elements. But yeah, it's an interesting problem, and I think in educational terms, that's an open question. I think that'd be one that is worth continuing to think about. I think in order to teach kids about complexity, we teach whole systems. And I don't know if you're familiar with the open systems model, but a very simple view of an open system is that it has an input. It goes inside of a system that has transformation and structural. So it evolves structure or grows structure, like animals grow or cells grow. And it transforms the energy from input. And then there's one output. So you only need 4 things to have an open system. 5. You need the environment. Because in the open system itself, the input has to come from somewhere. It's coming from the environment. It goes inside the agent. Here's where that agent whole system thing comes from. So it goes inside the agent, and then the agent has 2 jobs: use the energy and grow or change or remember something, and then put out into the outside world. That's the open systems model at its simplest. And that is a heart of complexity wasn't known at the time open systems became a science. And now complexity and chaos theory have evolved quite a bit more. But essentially, to my view, it comes from that same place. Okay, I'm going to quickly go to my PowerPoint. And then I want to just make sure that I'm sharing.
And I've sent the link to the article in the chat window, and everyone can access it. It's an open access article, I believe.
Yes, that's true.
You got lucky because that's not typical for British Journal. So
yes, I think I had to pay for that.
oh, okay. You didn't get lucky.
Yeah, you can nowadays. There's quite a bit of publishing that when you go through that part of the process, and they say, "Would you like it to be open?" Then I or the project or a group of people take on the sort of averaged out expense of letting it sit out there, and so we mix it. I like it because it makes things a lot more available.
Mm-hmm.
Okay, can you see this AI roles in learning? All right, I'm going to see if I can advance slides here. So modern AI, of course, as everyone in this meeting probably knows, is largely large language models. And if you go back more than a year ago, the world didn't have too many of them. But now there's a plethora of them. And so I've got a couple of slides about that, and then talking a little bit about what that how that seems to be evolving. And then we'll wind up with the AI roles in learning with that 3-level framework. So this slide is a view of artificial intelligence in which there's a branch in machine learning, there's a branch in natural language processing, expert systems, and then specialized branches for vision, speech, and so forth. And these come together in various ways. There are forms of artificial intelligence that use more than one of them at a time. The big advance that happened a year ago in November was that the natural language processing branch came on the scene and has run away with the store in a way because of how successful it has been in addressing all the things below: expert, vision, speech, planning, robotics. I'd say there's probably now just 2 streams: machine learning, pure and simple, and natural language processing in the sense of the large language models. And those models then are taking care of all the applications in expert system, vision, speech, planning, robotics, and on it goes, decision making, and so forth. Notice that in the natural language processing side, there's just a handful of core activities, and the same in the machine learning. And it's fascinating how fast the field is changing. And to my understanding, how quickly psychological models are helping to promote, advance the field. So the people from the computer sciences and natural language processing areas are actually mimicking a lot of psychological processes and making big advances. And I've got a couple of examples of those. This is just a slide about how big are the models. And this only started in 2018, as you can see. By the November that I was talking about is probably the GPT-3 release. And let me see where that was. I'm not seeing it out here right now, but the GPT-2 is noted here. Notice 1.5 billion, that's parameters. So if we do when I was taught science, it's like you need 1 parameter. You need to really simplify everything, and you have, here's your hypothesis, and you're going to look at 1 thing. Well, these things are looking at 1.5 billion parameters. So these are very big abstract spaces. And notice that up at the top with the in the top right, we're up now 600 billion, 1.6 trillion. And so, there's GPT-3. I finally saw it. 175 billion parameters. And so the parameter space is huge. And by parameters, you could think of those, that's your unknowns in a sense.
Is there a citation for this slide?
Let's see. This one, if you do a Google search for deep learning parameters, some of this came from, it's not an academic article. These would be the people following the industry. So things like the Gardner, I think is one of them. And yeah, okay. I should have done that.
So Ed did find GPT-3, one of my students in this class. He did. Thank you, Ed, for pointing it out.
Is that in the chat now?
Yeah.
Yeah, good. Yeah, I would encourage you to sign up and use it and give it a thought. Students are using GPT-3 to write essays, so we should know more about how they work and what the prompts are, how to use them. And there's a whole growing literature of using AI productively in classrooms for learning, and not just being unaware that they're out there, because one of the first uses of them is that it's a quick little essay machine. So the essay assignment that is almost meaningless to both the student and the teacher, those are not worth doing anymore. They probably never were, as Kurt would probably point out, but they're even less important to do now, because here's another view of the family tree, and I'm not going to spend any time on it, but notice that ChatGPT, the one that everyone's using, is just one of many, many, many. When I was in Australia, we were down in the lower left-hand portion of this tree playing with Bert and Ernie and the other folks. Yeah. Okay, I'm not going to spend any time on that, but I wanted to show you this.
Oh, can you go back a second? So if we can get this, your slide sent, I really recommend you all explore these links here. You might want to show one or two real quick. So it was fascinating. I was playing around with this the other day. Just show one or two of them if you can, David.
Okay, sure. Well, the whole idea that the way the language models are used nowadays is that we ask them effective questions, and that's called prompting. So the businesses that are effectively using AI are getting better and better at making good prompts. Now, one of my favorites is the chain of thought prompting. Zero shot prompting happened when computer scientists, if you know how models are trained, if you give a whole bunch of data to the machine and it learns that, then it can do pretty well with similar kinds of data. So that's training models. But zero shot means I've given you nothing to work with at all. And how do you prompt someone with zero or few shot? But here's one. I'm just going to see if I can make it go to this. So notice in this one, the standard prompting is that here's the input. Roger has 5 tennis balls. He buys 2 more. What is your answer? Blah, blah, blah.
We're not seeing that, unfortunately, but it's okay.
Oh, okay.
You know
Yeah.
how this Zoom works. It does.
Yeah, maybe when I shared, I didn't share my desktop. Hang on.
Right.
Now do you see that?
Yep.
Okay, so the standard prompt is on the left. The chain of thought, notice what happens here. The chain of thought model basically has a little bit of memory so that it's learning as it's going, but in a small way. And now chain of thought is much, much better than that. And this article I was going to show you next is an example of it. So at Stanford, this generative agent's interactive simulacra of human behavior, that's the name of an article by a group at Stanford. What they did was they made a game space that you're seeing, and they released little artificial intelligent agents in the space, each that had their own little goals. Like one of them was going to have a birthday on Friday. And it, independent, all by itself, with no rules and no training, went around to all the other agents saying, hey, I'm going to have a party on Friday. Can you come? And they started behaving like people and behaving like little, well, they had agency. Now, where did the agency come from? It came from this. This is the model that was inside of each of these. Now, notice when I was describing what an open system is, that it has input and it has some transformations and it has an output into the world. That's what they gave these agents. They gave them agency by building what they called a generative agent memory. And that generative agent memory was a memory stream coming from a planning process and a reflecting process. Remember the importance of reflection for getting growth to occur in a complex system. So you've got a planning mechanism saying, well, my birthday's Friday. I wonder if I should have a party. Then they gave it all of these capabilities and then perception and acting capabilities. So it's a wonderful article. The PDF of it is right there. Well worth a read. It's fairly new. I think it's just a few months old now. And it's Stanford, a group of folks that I think are really on top of the AI revolution. So I highly recommend it. What I wanted to point out here just is that the plan, do, study, act kind of cycle, they're using to advance AI in essentially a computer science paper. So here's a computer science paper in which we're seeing the action research cycle appear as the critical element of agency in the little AIs that are released. So this is agent-based AI, meaning that you've got a big environment and a lot of little independent actors, and then they go about developing their own intelligence from their own history of what happens in the site. So they would meet each other and have a memory stream of, oh yeah, I remember him. He mentioned he was having a party on Friday.
So this is an action research cycle, do you say?
Yes, the action research cycle is plan, do, study, act.
Right.
So plan, you can see,
Uh-huh.
the doing is acting in this case. That's where doing is. Study is the reflection. And actually, I guess the plan, do, study. So doing, I guess, in that version would have to have both perceiving and acting as what you do.
Right.
So you act and you see what you're doing as you're. So in the plan, do, study, act cycle, the act is your next plan, I think. If I'm not mistaken, in that original theory. So you plan something, you do something, you study what happened, and you plan again. And that's the act part of the cycle. Here, the action is taking place in the real world, and your perceiving is taking place in the real world. All the rest of this is taking place in your head. So this is their psychological model inside the agent, is the memory stream, plan, reflect, and so forth. All that's generative inside. And the thing that's different from between that and that, what was it called? Chain of thought. In chain of thought, there isn't a retrieved memory stream. It's just a very small one step back kind of problem. I wonder if anybody here has studied epistemic network analysis, ENS. Have you run across that? Anyway, they have
something like social networks, right?
Yes, in social networks, you come across it. It's by William Schaefer, and I mean David Schaefer. I can't remember.
It's David William Schaefer's University of Wisconsin Ed Psych Learning Sciences. My old department, where I got my
In his model, they've been looking at this issue of how long of a window do you use inside effectively the agent that's taking place, that's getting the meaning out of the network. And in his first papers, it was just a before and after, so kind of like the chain of thought. But I think he's now extending in a longer windows of time. All right, I think I want to leave this with you without, because otherwise we're going to maybe not have enough time to have people raise questions and first have a dialogue. This mapping here, though, is just saying that in AI work, especially in education, and especially because of the complexity, I think we're going to need human expert input at all times. The AI is helping, but it's not doing everything. Now, the human insight over a long period of time, as rules build up, a large part of human insight is remembered by the AI. So humans can do less and less and less over time, but still it's the human need and our sense of priorities and so forth, that those features have to be a continual part of the input. This is a diagram of some software that we've worked on over the many years, and it is underpinned by a theory from Educational Testing Service that started out with the making tests automatic. So the user is performing at an interface where you have these performance space variables. You guys would call that instructional design. Performance space variables are the instructional design, and someone's interacting with that thing. As you interact, it creates events, and those events are telling you things about the user. Ideally, in a really well-designed thing, the things it's telling you about the user is how are they thinking, how are they feeling, and what are they doing? What are they capable of doing? So if you get signals coming through for cognition, emotion, and behavior inside the interaction events, then you're able to say, oh, here's what we believe this person knows and can do just from the interactions that they're doing in the space you provided. The machine learning background of it, that's where the heart of the AI is that you use machine learning techniques with domain models and expert input to build rules that allow your user to have an adapted version of the performance space, or to get a new a new challenge in front of them. So this is similar to game creation. It's similar to finding the next item on a test that needs to be done. It's the same kind of cycle that's required in order to have an adaptive lesson design. For those of you who haven't seen domain models, if you look into evidence-centered design, ECD, by Allman and Steinberg and Miss Levy. The big name is Miss Levy in that field. This brings us to the 3-level framework, and I'm going to try to draw things together now that will span across what we've sort of introduced. There are 3 levels to the design: the learner as an individual, the learner as a member of a group at the middle level, and then that whole group of learners, the whole learning community, as a member of a culture. And toward that end, we try to bring together a few different theories and tie them together with mechanisms as best as we can and as much as we understand them. So at the individual learner level, there's an idea of the complex adaptive system that comes from complexity theorists and computational biologists, especially a guy named Kaufman, whose name is listed there. If you want to have a primer to Kaufman, read his book called Investigations. It's a wonderful introduction to his thinking, but he's someone who brought forward the idea of the cell as a network rather than just as a physical, so that a cell in a biological sense is more than the wall and the things inside the wall and the amino acids and so forth. It's a network of functions. So in the idea of the complex adaptive system is that intelligence itself at the universal level has come from somewhere. And what we're trying to do in this theory is to say, well, Piaget and Keller and others in the psychology of learning have paid attention to this cycle, this fundamental cycle that takes place, that brings the input from the outside world, brings it inside and does something with it to create memories and knowledge and capabilities, and allows the learner to do things in the outside world. So in the big circle, in the bottom right, what I've called the micro level of the individual learner, there's the theory of Piaget, that's the disequilibrium leading to assimilation, leading to accommodation, leading to equilibration. That's a process that was not the thing we mostly remember Piaget for is development, developmental psychology, kind of the progenitor of that. But this idea about how it happens, he gave us a roadmap to the mechanism. So in the article, you'll see a table that lines up how his theory talks about that. And I've tried to make a parallelism between that and Kaufman's noting of what the fundamental mechanism of evolution is. And evolution, by that we mean either learning or growth or both. You'll see above the arrows in the learner model is the Keller, I think of it as Keller, there's probably some other folks there too, but the ARCS, the attention, relevance, confidence, and satisfaction is often called the ARCS theory. And what seemed to make sense to us, the writing team, was that the reason for disequilibrium in your environment is that it gets your attention. So there are a lot of psychological studies of this. This is why when you stare at a dot on the wall will disappear and everything goes black. Your nerves are getting acclimated and they just fall asleep on you. Disequilibrium wakes you up and forces your attention somewhere. The next stage of doing anything with attention then is, do you recognize it? Does it stay a query that you don't know what it is and you're concerned about it or not? But something happens there. And then on the way toward accommodating it, you have made a link to the relevance of it. So you see a spot on the wall, oh, is that a dangerous bug or is that just a paint chip? And when it becomes relevant to something of interest to you, then you are at the stage of accommodation and so forth. Let me just kind of stop on that for a second, because if I'm raising a lot of issues or concerns, it might be good to see about that.
I'll just point out that, and if anyone's taken P540, you probably learned a bit about some of these theories, but also in our department in IST, there's a pretty big emphasis on the ARCS model. And so they've probably heard about ARCS before. And if you haven't, it's good that we bring it up here.
It's a powerful, yeah, it's a great model. Some folks have, I've seen some very good technology projects from Korea, actually.
Yep.
I used to visit there, and they were paying a lot of attention to whether technology use in the classroom or in a learning design, was it effectively getting attention? Was it helping the learner to build relevance? Was it then giving them practice opportunities for them to gain confidence? And then, was it really meeting a need so that they would come back and get more? That kind of thing. So it's a wonderful theory. We're proposing here, and there needs to be work done, because we're not just saying this is the truth. We're just saying, geez, it's interesting how these things could be aligned to make sense. And for me, one of the most compelling issues about what's taking place here, it's not on this map, is the Kaufman idea. And inside of investigations, what he did was take the internal combustion engine of all things, the Carnot engine, it's called. When I first found out about that, the big stumbling block to me was, well, not everything is physical. There's things that shouldn't, that wouldn't operate that way. And this takes us all the way back to my opening statements, that in a complex system, some things are physical and other things are information. And I've asked many physicists over the years, what's the relationship between the physical universe and the information universe? And you get a long conversation started by asking that question. Then, okay, so here's the slide. It goes into a little bit more depth of that. The point of this slide, and I'll leave it with you to look at in more depth, is that in order to meet the need at the point of disequilibration, we need to have AI making personalized recommendations. So if I, the learner, have noticed, oh, I don't know how to do this, I don't know where this is, or I want something else, I'm in that state of disequilibration, then it would be very handy to have AI noticing that and saying, oh yeah, have you ever thought of going into music? At the stage of assimilation, it's using learning analytics effectively to figure out what is going on. So how is this learner making sense of and making relevant the things we are presenting to them? And then when we do know a little bit more about that, what else should we do to be most effective in giving them the next piece of advice? If we use this page and just thought about something like, I play a lot of piano, I'm a jazz pianist. And so if I was teaching you something about jazz, I would probably be in one of these 4 states at all times during our lesson, listening to what you can do, making a suggestion about what I think it would mean, helping you make sense of it in some way if you needed a cognitive push, or if it's a physical push, or even an emotional one, so that my interventions would be tuned to what it is I think I'm picking up from the relationship. And then all along through that, giving you formative feedback as well as summative. So that's how we line up traditional aspects of pedagogical cycle with this level of the micro level of the learner. The harder words on this slide, and they're definitely harder for me as well, from the Kaufman idea, iso expansion and iso compression, adiabatic expansion and adiabatic compression. These are the 4 stages of the 4 cycles when you put the Carnot engine concept into a living agency. And that's so it's like a biological engine. So and it's helping to explain what happens when food comes into the system or other input, how that gets compressed. Compression, for example, I have a wonderful book on my shelf here called "What Is Mind?" I think What Is Thought by Eric Baum. He says that all of our words and symbols and everything we know is compression. So when we say cat, all of a sudden that compresses a whole body of experiences that I've had and that you've had. And some people might think I'm talking about a furry animal, and someone else will think I'm talking about a big yellow truck that pushes dirt around when I just use the word cat. Both of those come from the compression effect that having the word, what it means to have a word, to have a symbol, it compresses knowledge. So anyway, those concepts from Kaufman are things that I'm still certainly working on and thinking about in my thought processes.
David, I just want to point out, if you've downloaded the article, it's on page 1131, table 1 on 1131. He explicates on these different terms. We've got about 10 minutes before some people are probably going to have to go here. So do you have, not
Yep.
sure how many slides you have left.
Yeah, we'll just do it with about 1 minute per slide. I want to introduce you to the idea that came for me out of John Bransford's work. There's a very nice book called How People Learn.
And now How People Learn Part 2.
Yeah, there's a bunch of parts to it now, and it's also been applied in schools. Any of those are good, but looking at Bransford's work when he was with the National Council, there was a committee of people that worked together.
Right.
And the thing that I take away, I mean, there's a lot of takeaways from it, but what I've always really liked is this 4-part version of what a knowledge community is. So the knowledge community has people in it who know things, and they're capable of giving feedback to a learner who would like to join and become a part of the community. And so that you've got to deal with all 4 of these, and they're in a dynamic relationship. So I've enjoyed trying to think about when we say a community of practice or a knowledge community, how these 4 interacting pieces fit together. And knowledge in this sense is not the thing that's chiseled in stone. Knowledge is the growing leading edge of the field. It's how does knowledge come into the community, and who allows it in? Who are the gatekeepers? How do you know when it's there and it's not there? And if you say, "Oh, I know something," and the community says, "No, you don't," then you're not in these parts of the circle. So being a part of a knowledge community and growing through it, all of that's kind of covered by these concepts. So there's another table that looks at the AI capabilities that would help in these 4 arenas of building community. AI that nudges, AI that matches individuals, and so forth. I'll leave these things for you to think about. But note that there's like now 8 different AIs. 4 of them are here, 4 of them are on the other table. And if we go to the, and there's actually 2 positions here. There's the AI assisting the individual who's joining, and then AI assisting the community. So there's 8 total concepts of how to develop AI to help help a community of inquiry to get better at its job while growing its learners. And then the last thing are the 6 parts of the cultural historical activity theory. There's a lot of reading to do on that, and so we won't go into all of its details, but just note that there's 6 more different potential places where a specific task for AI is set out in order to play a role in the larger task of building cross-cultural, cross-community knowledge. I think that's good enough on really what the article tries to do. And of course, it's woefully inadequate to try to put all this into an article. Oh, yeah, the last couple slides, I think, take us off course, but they are evidence that other people are thinking along these same lines. So there's a guy at Tufts University, Michael Levin, who is one of the leading lights in this area of matching up technologies with the way biology works. So it's biologically inspired technology. And part of what I've been sharing with you is kind of a biologically inspired view of the role of AI in learning theories, inspired by what we know about the underpinnings of biological learning by individuals.
So David,
Yep.
let me just point out that you talked about John Bransford, who was influential on my career and many people's careers actually when he was at Vanderbilt before going to Washington. He passed away this past summer. But if you had, yeah, really
I hadn't heard that. Yeah.
Yeah, I think he might have had Alzheimer's. I'm not positive. Something that
Hmm.
dementia. Anyways, he's very famous for this thing called called anchored instruction and creating macro
Yeah.
context for learning. He
Right.
used Raiders of the Lost Ark videos to teach math and science concepts to kids in schools. Looking at how many Indiana Jones is the pit wide, or could he replace the golden statue with a bag of sand and all this stuff? They do all these what ifs on that. And so, he create what's called, can create short videos, and you can do this today with CNN videos, BBC videos, to anchor the learning in a short snippet of content and stuff like that. So if you took 511 with me, R511, you would have heard of Bransford because we had these articles on communities of learners and situated cognition and all this kind of stuff. Bransford worked with a person named Anne Brown to do that How We Think book, and she's another famous person in the field who created reciprocal teaching, where kids become the teacher, and other things. So that, and I think the third author is Cocking. I don't know what his first
Cocking,
name
yeah,
is.
right. It is Cocking, yeah.
Yeah. So then there's a new version of that book that they use in P540. If you take P540 now, that's the book you'll use part 2.
Oh, that's really nice.
So thanks. Yeah.
That would be highly recommended. It's what is fabulous about that is it's a retrospective view of the last 25 years of cognitive science.
At least.
Yeah, pulled together effectively. Yeah, probably the whole history of cognitive science.
Yeah.
But pulled together very effectively into a single model. So you really get the cognitivist perspective in its fullness. What I always liked the fact that he spent a lot of time on metacognition in that book.
Yeah.
And I work with a guy named Roger Azevedo from University of Florida, or I think it's University of Florida, on metacognition in a technological venue. So how is it that when we're planning learning environments and learning interactions, can we really focus on what is the kid getting about themselves out of this? How do we know they're tracking on how they're thinking and how they're taking the problem apart? In other words, don't focus on the knowledge that's supposedly being transmitted. Just try to see whether or not the student is thinking aloud, and can they share their thinking aloud in such a way that we as instructors or the environment with AI can respond to where they're coming from at all these points. And the way I think about it now is that metacognition is the reflective loop. So that's in the middle of that reflection loop, without which we wouldn't have any complexity at all. It'd all be a one-way street, and we'd be, dumping knowledge into the blank pages of the kids' heads, which we know does not work.
So I'll come back to that anchored instruction notion, and that if you watch a common video or have a common experience, you can come back to it and replay it and have metacognitive types of questions around it, and reflective activities and peer-based activities also. So look up the concept of anchored instruction or macro context. So the macro point of view you had up there earlier. The other theory they had at the end there before going to the biological slide was related to Angerstrom's notion of activity theory.
Yeah.
So so if you want to get, it's complex. So you don't want to just dive in right away, but it's based on Vygotsky's work and trying to look at how people learn in the social plane and how the interactions that one has with other tools and signs and other human beings, more knowledgeable peers, more knowledgeable experts, can be internalized that social experience can be eventually appropriated for your own purposes, and then eventually internalized for your independent problem-solving behavior later on. But there's a lot to it than that, and we don't have time to justify, I mean, to explain the entire model. That's an entire course of social cultural theory or social constructivist theory in nature. But anyways, I just want to point out that last slide was related to activity theory. So if you're looking for something to want to look up and read more about, I would read more about activity theory. So we have questions for David. Yeah, that slide with the artifacts, objects.
And I'll just point out that Vygotsky gave us the top 3 circles, artifact, subject, and object, and Engstrom gave us the bottom 3, connected it together, and expanded the conversation. So that's...
Yeah, and Vygotsky's colleagues, Leontev and Luria, Vygotsky died young. He was 36 or 37. He was born in 1896, died in 1934, whatever. There's his colleagues who fleshed out the model. He had the basics up there, but they worked 40 years to try and get to that, and push the theory and look at what's happening in those activity spaces. So anyways,
I've used that activity theory as an analysis framework for game-based learning. Yeah. And it's very effective in that regard, because each of the nodes in the activity theory framework tells us something about why it is that games work the way they do. Yeah. What you give to the person, what they're doing as they're enacting through the game-based interface. So yeah, there's a lot of richness there.
Yeah, I had a student who studied, we were looking at teacher about change when we started. She was looking at school the change process that was happening in a technology integration project. And she did an entire dissertation using activity theory. I've had a couple, but then I'm doing a book on it. So her name's Lisa Yamagata-Lynch. She's a professor at the University of Tennessee at Knoxville. If you want to learn more, you can look her up or meet her at ACT conference or other. Do you have questions, Bo, on the Jamboard that we need to bring up?
Yeah, we have I think about 3 or 4 on here right now.
Who wants to jump in with their
maybe
question?
5.
Okay, we've got a number of questions. Who wants to jump in first? Okay, go ahead. Of course, Rachel.
Okay, so would you characterize this complexity concept as being based on objectivist epistemology?
That's interesting. No, I don't think so. If you are interested in the historical roots of it, look at the Santa Fe Institute. So the Santa Fe Institute brought together physicists, psychologists, systems theorists, and others over a long period of time. There are many good publications from it. They have a summer series. I would say that it's an attempt to understand why it is that traditional science has a hard time answering some of the hard questions. And so it doesn't argue that that traditional science is not the right way to go about stuff. It says these systems are unique. And I think it was highly influenced by the complexity of biology. The biologists really got us to this forefront, but the computer scientists who were fiddling around with AI from the beginning and sort of organizing through code how we think. If you remember Alan Turing's fundamental work, the computer of his day were people sitting at desks fiddling with numbers and doing calculations. And he thought, well, surely there must be a better way to get a machine that could do the calculation. And his Turing machine, which is now sort of the smallest, most compressed model of what a computer is and what computer science is really fully all about. I don't think of it as an objectivist point of view, although it does have, it's rooted in objective reality in the sense that things that can be, if you can't write I think it's called an effective procedure. If you can't make something into an effective procedure and talk about it, then it's kind of a hooey in a sense. But yeah, so there's a form of objectification that's taking place, but it is not just saying there are no mysteries because fundamentally that this issue about the complexity that I was showing you with that spreadsheet is that you cannot predict. We can know everything there is to know about that little system, and we will not be able to predict what happens if you add one more number to the far end of the numbers sequence. It's just impossible. There's a scientist named Stephen Wolfram who invented Mathematica, and he's been working on this for a long time. He wrote a really big, thick book called A New Kind of Science. So his point on all this is that certain forms of unfolding in the universe just have to be unfolded. You're not going to be able to sit and think about it ahead of time and through our logical calculus methods get there. It cannot happen. There's an uncertainty. So yeah.
Stephen Wolfram created, I think it was Wolfram Alpha, where
Yes.
kids could look up answers to all their calculus questions and algebra questions. That was a kind of predates this now ChatGPT era. But I always found it fun. I think he's a University of Illinois professor. He proclaimed himself as the next Einstein. And then at that point, I had my doubts, you know. So Emily Verga might have a question. Emily.
It looked like she might have to jump off. She left a message on the chat that says that she's taking away that the purpose of assessment and the importance of feedback loop in learning in both humans and AI. Yeah, we talk frequently about feedback. Seeing it in the models solidified some things related to metacognition and ensuring students have feedback to assist them. Yeah, I think that she's really got it there for sure. And that's what we're learning from all the modern AI is that it is learning. It has to sit there and learn, including learn as it goes and learn as things change. And it's one of the big problems is in order for it to act and not get unstable, things have to be knocked, sort of locked down. And that's where the subjectivist problem comes in. As soon as we lock it down, then it no longer relates to the real world. Einstein pointed that out too, even with mathematics. He said, it's a beautiful thing and it's perfect insofar as it doesn't relate at all to the real world.
So we've got someone in China. Shufang is early morning in Thailand and in China and in Japan. So welcome early morning. She needs to head out. So thanks, Shufang. We have time for, you want to say hello? Unmute your mic, Shufang.
Yeah, thank you. Thank you, Eric, Dr. Gibson. All reminds me all the readings and studies in Dr. study years in Michigan State.
Oh yes, yes.
Theory, etc. Yeah, thank you, everybody. Yeah, it's very, 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 very interesting, very deep and complex to me.
Great. Well, thank you for that good word.
Yeah.
Shufang's at SUNY Cortland in New York. We have time for two more questions. I know we got 3 or 4, so make sure jump in here if you want to make sure yours is asked. So just go ahead and unmute.
I think Ed should ask his question because it relates
Ed,
to one of the other questions.
Please, Ed. Very active in Canvas this week, Ed. Thank you. Good discussions. Is Ed still here? Are you muted, Ed? I don't see Ed. He might have
his question was, is there anything designers can do to affect any of those factors, R prime or Rx, one takeaway X, in the calculations that you were using at the beginning?
Yeah, well, I think designers are completely responsible for the R. And then I think they have to design with some kind of model in mind of what the X is, because the X to me is the learner coming in with preconditions and whatever their entering point is. The R is the design. It's the shape of the space that the learner is in. So I think, yeah, that's a great question. For me as a designer, I tend to keep my head in the clouds probably too much. I would probably try to dip into all the theories that are on those pages of some activity theory knowledge about, well, if I'm making a tool, what is it I think that the student is going to do with it? What's going to be their objective versus my objective? Will we see eye to eye on that? Will they envision that they're a part of a community of some kind? Can I make them feel like they're part of a community? Can they learn from the community and from peers? So I asked myself a series of questions using these same theoretical foundations to just say, have I got parts of my design in which I've considered that part of the impact and how and what it might mean to the learner as well as the whole process.
Thank you. Anyone else? We have time for one more. Please jump in if you didn't get a chance to ask. Jill is stopping herself from asking. Does anyone besides Jill have a question?
Can I call on Carol?
Please, Carol.
But my question has been answered already.
And what was the question?
It was
Oh,
what were the 5 emotional underpinnings? And
Yeah.
Rachel answered it for me. So
Yeah, very good. Yeah, it's the 5-factor model. You can look up FFM. And if you like, there's a particular approach to that called circumplex theory. And there's an article by Hofstee, Hofstee, I believe, and others, which uses the 5 and it pairs 2 at a time. Like it says, well, what would happen if you have openness and agreeableness? And it makes a circle of that and it describes the keywords of those 2. Then it does it for neuroticism and openness, or neuroticism. They looked at all of the pairs of those 5 and they built circumplex models and looked at that in language about the key words that are there. And it's interesting that anytime you do a circumplex, you have a circle and you have 2 dimensions. There's a horizontal and a vertical. And so if the vertical was openness and the horizontal was agreeableness, let's say, halfway in the space somewhere. So they have these dots of words that are appearing out in space, showing us a little bit about the valence of the meaning of a word related to that part of personality theory. Very, very interesting article. I tried to get some of that going in the AI in simSchool, but of course we have a long way to go on that. But I had envisioned a day, and now we could do it, where the words themselves that are sitting out there in those circumplexes are pinpointing a particular profile at that moment. So and now with large language models, it should be sort of rolling off the log backwards. I just need to get a $3 million grant to play with it.
So is your sim project, your simSchool project, a viable one, or is it always, the budget's always, you're not year to year, month to month, or?
Oh no, it runs. Yeah, it's been running for 15 years on its own. Yeah,
Okay.
it's totally. Yeah, it runs. I'm just talking about for how it could evolve in the future.
Right. How
Yeah.
many schools would you think it's been adopted in, or how wide is?
Well, at one point we had, I think there are currently about 10,000 users in different locations around the world.
Wow.
We've, depending on which, I think there may be 200 higher education institutions who are using it in one way or another. During COVID, there was a huge spike because people wanted to have school placements take place inside simSchool instead of real schools.
Yep.
And so they were using it as an actual practice zone. And so there was a spike during those years.
Yep. My first doctoral student at Indiana back 1992, he took 14 years he took 7 years to take courses and 7 years to dissertate. He created simTeacher. And he spent a lot of time testing at UT Austin. And when he got done, he decided to become a flight attendant for Southwest Airlines so he could run marathons in different cities. So, he spent all this time working on his dissertation. And if you design a system, it takes a while. I don't recommend it. I recommend evaluating simSchool, which exists already. Don't build your own. Jill, I know, has a question, but make it simple since you're the last one and we want to end tonight, Jill. At least I know you want to say something. I've seen you smile 50 times. So go ahead, Jill.
I would like to thank Dr. Gibson because I got so many inspiration from today's lecture. For example, I did a systematic literature review on my digital co-creation based on the triangle. I mean,
Yes, on
yeah,
activity
and
theory.
also, I have done the community research, and also I have done the prediction research. But today I just found out what I have done is just scratching the surface. So you just
Well,
dig into the-
welcome to our
Yeah.
world. No matter how long we take at it, we will all be scratching the surface.
So Jill's a
Thank you,
legacy.
yeah.
She's a student of a former student in our program for 20 years ago and has published in
Yeah.
top tier journals before even finishing her doctorate. So she's a visiting scholar here this year at IU, along with Alicia and Lena, who are my other visiting scholars. I want to say, David, it's been a delight to have you with us tonight to present your recent article to us. And now we're going to read it and discuss it in Canvas this week. So please, everyone, write some quotable quotes down and put them in the Canvas. I want to also say that when I was growing up, there was a song that's very popular on the radio. It was called "The Cisco Kid Was a Friend of Mine," and only Rachel will remember that song. But you know, the Cisco Kid was a friend of mine, goes on and on. But I have the UNESCO chair was a friend of mine. So David is the UNESCO chair, and he is a friend of mine. He's a friend of all of yours as well. I'm not going to close this just quite yet. I want to see if anyone wants to unmute, since this is the last session, and say a 3, 4, 5 words to close, either to David or about the sessions we've had. If anyone would like to jump in, and maybe we can go all around, just say a quick, and Susie Parn, why don't you start? Say a quick thank you or whatever you'd like to say. We'll go to different people. So start, Susie Parn.
Thank you. I'm actually typing. Thank you so much. Well, thank you so much for giving the talk. It's very fascinating and really opened my world. Really new information and a lot of things to learn more. Maybe I'll contact you some of the feedback AI, and yeah, very thank you so much.
Tell them where you work in Thailand.
Right now, okay, I'm working in the Institute for Innovative Learning in Mahidol University, and I'm instructor here. Yeah, and my project is related to teacher professional development. So it's really actually match what I'm looking for to improve their feedback to the student. Yeah,
you might use
applying for.
You might
Yeah,
use simSchool. So yeah, there you go. We have a couple of psychology professors. I'm sorry, cut you off. Christy, would you like to say a few words from Western Michigan in the community?
Sure. Sorry, it's been a long day. It's Thanksgiving week, you know. I just was really happy to hear the integration of so much psychology into this talk. The article as well. It is, like Dr. Bonk said, it's my passion. It's also my, background, but I think it's deeply rooted in learning. So it was really refreshing to see that, even though your statistics gave me a little PTSD to my stats class, but I'm okay with that.
So Hal, another psychology professor from Indiana University in the Southeast campus in New Albany.
Yeah, thank you, Dr. Gibson. It's just so interesting because in your talk, you mentioned so many psychological theories, and it just opened to my eyes how they are applied, really lay the foundation for the AI, for what people are interested today. And so it just changed my mind about the theories, and I think I will give it more life where I teach it to my students.
And also in Indiana University, in the eastern part of the state, in Richmond, Zihang Zhao, another graduate of our program, Dr. Zhao.
Hi, thank you for inviting me, Dr. Bond, and thank you, Dr. Gibson, for the presentation. Personally, I'm very interested in learning analytics, and right now I'm managing a very new program. Is called a Learning Analytics Faculty Fellow Program, and I'm reviewing faculty applications and hopefully pick one or two to work with me on learning analytics projects. So thank you for reminding me of the ARCS model today. Yeah, I mean, I learned that before during the PhD study, but now I think, wow, that's fascinating. Actually, I can, like relate it to the AI related, projects, and then, use it in our learning analytics projects. And thank you so much. And I really learned a lot today.
Si Young finished her doctorate a year ago and decided to get an MBA or learning analytics business degree, master's degree. So she re-enrolled. So Amelia in Japan, it's early morning there in Japan. Amelia, like to say something before we go?
Yeah, I'd just like to quickly thank Dr. Gibson for speaking with us today. And I knew I was in for a treat when you brought out your Excel spreadsheet and called it a fun tool you can play with. So I've been just researching AI on the surface a little bit, but today I'm like, okay, we're going there. So thank you very much.
Yeah, I was looking at, you said one, you put an R of one, they tend to die out, I think it was. And I was thinking, well, there's some politicians that like to give a 1-2 right now. Anyway, no politics. Anyways, Evan from the Coast Guard, Evan, who's in DC area, I think, along with Rachel.
Yeah, thank you for the great presentation, Dr. Gibson. I think I have about 10 now open tabs on my Internet Explorer from your article, Chaos Theory, Open Systems Model, Circumplex Model, the parameters of deep learning. It's all great stuff and a lot to think about. And thank you for personally responding to my email and the kind words as well.
Also in DC is Rachel.
Yeah, I just was putting some words in the chat, and I'll say them out loud. Integrating theory and application while sparking some new thoughts. And this presentation was fantastic, and thank you so much, and fit in perfectly, and maybe an ideal capper to the course.
Sounds good to me. Vera, my former mentee, who I met in Beijing when I gave out the rubber chickens, she was in the room sitting on the floor near the front of the room, and that was like 2004 in October. Everyone in Beijing wanted a rubber chicken. Vera.
Oh, thank you, Dr. Gibson. It's a very exciting presentation, very enlightening. I actually went to Center for Institute summer school before 2 decades ago. So cool to listen to your presentation. And I'm actually recently helping a research study about leveraging learner agency in ITS design. So, like we found some interesting impact. Like we were trying to figure out, whether we should advocate human and ITS collaborate in decision making, and then we found like it was also moderated by students' self-regulated learning skills. So a lot to explore in the field, and I'm looking forward to read your paper. I might follow up with some questions.
Thank you. Ty, would you like to say hello?
Yeah, hello. Thank you, Dr. Gibson, for the presentation. I always enjoy hearing about AI. Like, I'm pretty new to using it, and I've only used it a couple times, but just being able to see all the implications and seeing how important it can actually be in education and in anything, basically. Like, it's really cool to me because, like, I would have never thought that we would have been at this state in our lives to where we can actually use something like this, and it's an incredible tool.
Ty's in our certificate program for online teaching and learning. He's also a pitcher in our IU baseball team. So he's thinking about how he can use AI to enhance and improve not only his pitching, but other people's, and become a better coach in the future, I think. Right, Ty?
Yeah, just being able to, use AI, and also just being able to use more remote training is, becoming the new thing for sports, and definitely for baseball. So I think like that's why I really enjoy the talks that we've had in this course, and the other couple courses that I've been taking for this grad certificate. It's been really interesting, like learning all the different stuff that I can use for, wherever I want to go.
Thanks, Ty. And I see we just lost Carol, but it's been a pleasure having Carol in this class here, and she's put a little note. she feels honored and humbled to be part of this group and have great guests. Good night to you all. She's learned a lot, and she's just scratching the surface. We have just a few more people here. Lena, just 20 seconds, Lena.
Hi. Greetings from Chicago. I'm in hotel of Chicago. But it's so pity that I missed the earlier part of this talk. It's very, very impressive. And I'm very interested in this topic. So I feel regretful for that. Oh, I will watch the video for that and also read all those resources and articles. And also thanks to Dr. Gibson. Your talk is very, inspiring for me. And now I'm doing a project with the local bureau about how to encourage the teachers from middle school to use AI, use the technology to help them to learn and to teach. So I think your theories and research are very helpful for me. So I will read all those articles. And thank you very much. And thanks, Dr. Bank. You always bring this, very, how to say, famous or very, I'm so excited. I don't know how to express my emotion. So
we'll have lunch when you come back.
Yeah, very. But I think I miss a lot because I come to Chicago. I miss some talks about your talk and Dr. Gibson's talk. So
they're recorded. They're recorded.
Make up those things.
They're recorded. You'll get the link to all of this. No worries at all. So Lena's a professor of English in China. She's my visiting scholar, along with Alicia. Alicia, and then Bo gets last comment. Alicia, real quick.
Oh, sorry. Okay, thank you so much, Dr. Bank, and thanks, Dr. David Gibson. And I think that your research provides a rich and insightful analysis, and I learn a lot from you. Thank you.
Thank you, Alicia. She's also an English professor in Shanghai, and her second visit, tour of duty here at Indiana. Bo, I've already said it, my thank you. So again, thank you to everyone here. And Bo, would you like to end this?
I was just going to say this semester was even better than last semester or last fall. It was fantastic. I was thrilled with the guest speakers that we had every single week, and I loved all of the interactions that the students and I were able to have with them. Let's see here, who said this? Vera just said, Dr. Bonk's role in community facilitation cannot be replaced by AI, and I will reiterate that as well vocally for all of us here. Thank you, Dr. Bonk. Thank you, Dr. Gibson, as well for spending time with us. We had a great time this evening. We learned so much from both of you guys.
Can I get everyone to do that? World is open, so I can get a picture of this. Everyone, arms up in the air. The world is open. All right, 1, 2, 3. Great. Thank you very much. Thank you all. I'm going to end this recording at this point and stop the recording. It's going to the cloud.